Hello. Sorry. I need a cameraman. Here we are back at it again, and today we're going to add to what hopefully I got through beginning of today in class is more about finding limits. Hopefully we were able to establish how to find them graphically. So I'll check off graphically. And we have two ways left to find limits, algebraically and numerically. Alright, we'll leave the best for last, so we'll go to numerically next. So I'm going to figure out how to do the same thing I showed you how to do today with a graph with no graph. And we're going to do it with numbers and basically sissy charts. Sorry to insult, but that's the way it is. So numerically is what we're looking at now. So suppose I have this function, and recall you're writing it down. This looks a little crooked. Alright. You're writing this down in your comp book, and if you forgot your comp book, give me a break. First day, just write it on a piece of paper and bring it in. You will not get credit for this lesson until I see the notes. So let's look at this function, write it down, x cubed minus 1 over x minus 1, and I'm wondering about the limit of that function as x approaches 1. So, looking at the denominator there, I see something strange happens when x equals 1. So what is the limit? And again, we established graphically, and it's true and numerically and algebraically as well, is the limit has to be the same from the left and the right for this to happen, for this to have a limit. So numerically, we're going to have to look on both sides. So as I approach 1, I need some values. So I made a sissy chart, and I have to come up with the values myself. So as I get closer to 1, I started pretty far away at 0. Then I got closer to 1 at 0.75. Very close to 1 at 0.9, very, very close at 0.99. So I thought those numbers would give me a picture of what was happening to this function as I get closer and closer to 1. You would have probably picked other values, but you should get the same answer. So I put these into this function, and 0 yielded a 1, 0.75 yielded a 2.3, 0.9 yielded a 2.7, and 0.99 yielded a 2.997. So I think you can see where this is going, but we're not sure the limit exists. This is getting closer to 3. So if this does, so you can see I'm coming in from the left here. As I'm approaching 1, 0, 0.75, 0.9, and 0.99 are coming closer to 1 from the left. Now we're going to press in from the right, and the numbers I chose were these, and you will probably, on your problem, if you were asked to do this independently, you would have picked other numbers, but hopefully you would have something that proves the same number as I get. 3.8, 3.3, 3.03, and 3.003. So here we are, getting closer to 3 from the left, and now getting closer to 3 from the right. So numerically, we have observed that the limit does exist, and the limit as x approaches 1 of this function is 3. Now, if you find that this number differs from that number from the left and from the right, then we say it does not exist. Alright, so you try one. You try the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2. Alright, so you're coming up with a sissy chart, so turn it off or pause and establish a numerical chart. 4 will probably be a good number of values to put on your chart. Go from the left and from the right. So you can turn it off. I'm going to put in my results now and see when you turn it back on, see if they match. I came in from the left at 1.75, 1.9. I came in quickly, 1.99 and 1.999. And my values I observed are these values, and notice they are getting closer and closer to 1. Let's see if that, closer and closer to 1. On this side, from the left, from the right, I came in 2.25, 2.1, 2.01, 2.001. And as I did that, so I also came in to, it's getting closer to 1 from the left and the right, so therefore the limit does exist and it is 1. So make sure that you check from both sides when you're doing it numerically. Alright, these two examples will bear you up through any that I ask you in the future similar to that. So numerically finding limits. Alright, let's end our day by looking at the algebra. I'm only going to take a pass at this because there's really a lot I need to say about limits before we establish them in total algebraically. But I don't want to take the time on our first night to have this really long video. So I'll just go ahead and introduce it and show you some basics of the algebraic. Most of the time, this is the land you'll live in when you're finding limits. You will not find them graphically or numerically, and you will find them algebraically. So let me go ahead and establish some ways to finding limits with algebra. So, algebra, the first way we do it is substitution. Substitution is hopefully the way that will get you the limit, because if it's not, you have some other hoosdruk to go through. So let me give you an example. Say we have the limit. Again, we're not looking at the graph or a chart. We are just looking at the algebra. What is the limit of this function, x over 2, as x approaches 10? Substitution means you simply take the value that the limit is going toward and plug it in algebraically here. So we get 10 over 2. And if that creates everything that's mathematically sound, then 5's the answer. So that is the limit. Now I know we never get to 10, but we're getting close to 10. And if we can put that in, then this means we're getting closer to 5 with the limit. So that's the limit. So we never reach 10, we never reach 5, but we get very close. So if we can algebraically make the substitution and create a mathematically sound expression, we have the answer and we're done. So substitution is what you hope for, and you always check for it first. But what do I mean mathematically sound? Well, here's what happens, say, in this example. Let's suppose I was looking for the limit as x approaches 1 of x squared minus 1 over x minus 1. So if I try the substitution method on this one, I put in a 1 here and I get a 0 on the top and a 0 on the bottom. So 0 over 0 is indeterminate, so we don't have a sound mathematical answer, and I need one. So we have to pull out number 2, and that is factoring. Factoring will often get you where you need to go, but not always. So let's look at this one because it will help. This is a difference of two squares. A squared minus b squared factors a minus b, a plus b. So in this case, we have x minus 1, x plus 1 on the top, and on the bottom, x minus 1. Now, simplify that. When you have the same factor in the numerator and the denominator, they will create a big fat 1, so I don't need to write them. And I have x plus 1. Now I can use number 1 and substitute 1 into this expression, and which is algebraically equal to the original, but now I have removed the problem of the denominator with an algebraic step. So when I put in a 1 here, I get 1 plus 1, or 2. And if you check the graph, or you check the numerical chart, you'll see that it is 2. Alright, and the third and last thing for this evening, we're going to have 2 minus the square root of x over 4 minus x. So looking at that example, we will see that when you put in 4 for x, you get a 0 in the denominator and a 0 in the numerator. So again, you have an indeterminate answer. So substitution failed. Can we factor that? I know it's not a way to factor that. So often when there's a radical in the problem, it's not factorable. So we are going to use this strategy. Multiply by the conjugate. So the conjugate of is always related to two terms where the middle sign changes. So I'm going to take this expression, and since the radical is in the top, I'm going to multiply by the conjugate of the numerator. So it's going to be the same two terms except the middle term, the middle sign changes. So why would I do such a thing? You will observe the magic and power of the conjugate after we multiply through. So we have a binomial times a binomial, so it's 4 steps. 2 times 2, 2 times square root of x, minus 2 square roots of x, thus the magic, and square root of x times square root of x is plain x. And it takes on the negative sign because we have 1 negative and 1 positive. Here's the magic right here. That is why we multiply by the conjugate. When I say multiply by the conjugate, I mean the conjugate over itself, which again is a big fat 1. It doesn't change the problem at all. So this cancels out and it leaves a much more usable, user-friendly 4 minus x on the top. But then on the bottom, we actually, I think that, alright, I'll go ahead and multiply it out. Yeah, sometimes just to speed it up if I can. No, I guess I do have to multiply it out, yeah, because we're approaching 4. Never mind. Alright, 4 times 2 is 8. 4 square roots of x minus 2x minus x square root of x. Alright, so hopefully that will do something for us. It does not, actually. If you put in a 4 there, you get 8 plus 8 minus 8 minus 8. So you can still get a 0 from the denominator. So, but we still have done it correctly, but multiplying this out did not take us any closer to where we need to be. So I'm going to leave it factored, and if I stood back and looked at this, I would have known. Notice what happens when I leave it factored. Here we have the factor in the top and a like factor in the bottom. And so it becomes a big fat 1, and we end up with 1 over 2 plus square root of x. So what's the limit of that as x approaches 4? Hopefully, by multiplying through by the conjugate and canceling like factors, we will have an answer that works. 1 over 2 plus the square root of 4 is, that's 2, so 2 plus 2 is 4, and I get a 1/4. Alright, so I'm going to stop there with those 3 strategies: substitution, factoring, and multiplying through by the conjugate. There's more I have to say on this topic, but we will leave it for another day, another evening, and I'm going to stop there.